Good morning, one and all. This is Srinath from EC section team. In the subject digital system design, I would like to share about the EDA and quantum computing, a symbiotic relationship. Coming to introduction, quantum computing is potentially one of the most transformative technologies of our times. This is because it offers a new model of computation that is based on quantum physics and is fundamentally different from that of current systems that are built on classical laws and Boolean algebra. There has been a flurry of results recently that has provided credence to the thinking that the technology has moved from a basic science problem towards an applied science or engineering one. The field has progressed from proof of concept demonstration to quantum integrated circuits with over 50 qubits. John Preskill coined the term noisy intermediate scale quantum to, to this era when in we are far from a universal quantum computation but have enough quantum states, albeit noisy, to potentially demonstrate quantum advantages in hardware. And the two most popular physical realizations are perhaps ion trap and superconducting qubits. Each has its pluses and minuses. Therefore, companies are betting on different realizations and no one solution has won the race at this time. In this paper, we will consider superconducting qubits as this can be fabricated in silicon using the same technology that we use to manufacture classical hardware today. So, many consulting firms have started evaluating this technology and have forward their projection from 18 to 20. Boston Consulting Group estimated the business of quantum computing will be about 2 to 5 billion dollars by 2024 and reaching towards between dollar 25 to 50 billions by 2030. It further projects that it will reach 450 to 850 billions dollar annually in due to course. These indicate that in the near term 3 to 5 years, the impact is likely to be in the broader area of quantum chemistry, optimization, machine learning, and in finance. The question is what is the impact of quantum computing on EDA? EDA is a unique industry in that it is perhaps the only field that cannot only potentially benefit from the technology but also contribute towards fostering it. EDA has immense knowledge and skills when it comes to this problem of scaling to larger design. This is due to decades of classical hardware design, automation, and algorithms that emerged from it. And the question is what is the impact of quantum computing on EDA? EDA is a unique industry in that it is perhaps the only field that cannot only potentially benefit from the technology but also contribute towards fostering it. EDA has immense knowledge and skills when it comes to the problem of scaling to large designs. This is due to decades of classical hardware design, automation, and algorithms that merge from it. The, this this can potentially be leveraged by quantum computing designs. Here we come the general purpose about the EDA. Here, general purpose of the EDA universal quantum computer can be achieved only by the application of error correction and fault tolerant techniques. This requires that a logical qubit be encoded using a multi-physical qubit where the information that we care about is stored at logical level and physical qubits essentially provided re- redundancy. See here, it is a logical circuit about the EDA and quantum computing. See here, when it transfers from 1 0 to 1 2 3 4, and automatically in the next line it will transmit it to 1 to 10 and 5 to 6. These are the process which the EDA quantum computing is consist of. They they exhibit some characteristics that need to be accounted for in any solution using them. See the first what is that? In this EDA characteristic, limited connectivity. What is meant by limited connectivity? The qubit in NISQ devices do not have connection to all qubits, so A two qubit operation between distant qubit requires a series of swap operation to get them to neighboring qubits and then perform the required operation. Then second is short circuit depth. How the short circuit depth is consistent in the EDA. See, NISQ qubits are noisy, which means that they will lose their quantum state in a reasonably short duration. This puts a limitation on the amount of compute that can be done, and the algorithm that we want to implement in hardware needs to fit into this. And the last is about qubit noise variability. The qubit noise variability is that nothing but the noise characteristics of individual qubits vary and they are not equal. In fact, the noise characteristics of a given qubit can vary over time. See here quantum value. This quantum value is consists of uh, s- uh, uh, this quantum volume is consist of some other variable characteristics involved in it. See here circuit optimization, coherence and crosstalk gate fidelity and number of qubits and calibration errors, spectacular errors. These are the quantum uh, volume which is considered with characteristics. See, coming to design a bitter chip. What is design a bitter chip is included in EDA. See, first there is a quantum chip itself, the number of qubits, its connectivity, and the quality of each connection are key parameters that derive QV. A key area of research is to come up with better coupling maps that allow for more qubits to be coupled with less crosstalk. This will ensuring that the qubit has a low error rate and a long coherence time. See in this also we have observed one of the quantum volume, that is qubit and qubits and crosstalk. See, electromagnetic field simulates like HFSS are good for the detailed simulations but not necessarily fast enough to prune the solution space of possible topologies. When coming to static mapping, an area where EDA algorithms can play a key role is in the mapping of algorithms to quantum circuits. Simple algorithm focus mostly on the connectivity map of the quantum computer, where since there are only a limited number of qubits and there is only a limited amount of time to complete a computation. Good circuit optimization and mapping can make a huge difference to whether an algorithm can run on a current NISQ machine or not. See, here is a tabular form about the uh, yeah, tabular form about the quantum volume, which were consisted with single qubit error and two qubit error, defacing time and relaxation relaxation time, where it mean it was consisted with three types of characters, that is mean, best and worst, in terms of Tenerife, Tokyo and IBM. These are the steps we can see in the tabular form. And coming to circuit presentation, how the circuit presentation is done in EDA. Decomposition in terms of uh, CNOT's swap gate is costly in superconducting qubits like IBM's, as it takes the three CNOT gates to perform a single swap gate. And coming to quantum deep learning machine, and deep learning have had a big impact on business in the last decade and continue to do so. On the quantum front, there is a new way of results that have come about in the recent times that has pushed quantum machine learning as one of the important applications to watch for in NISQs. See, coming to symbolic relation, what is what this symbolic relationship is meant for. See, quantum computing is a very promising technology that is at its infancy right now, but has potential to disrupt many businesses in the upcoming year. The compute program is nothing but quantum volume increases is following an exponential trajectory like Mori law and is projected to continue. We have entered the NISQ era, where we have only small number of noisy qubits to do useful work. The challenge is to maximize the quantum volume, which quite some papers have been published that address optimization of individual matrices. They need to be optimized collectively to have a real impact on the quantum volume. The EDA community has a long experience in computizing for many conflicting objectives such as timing, area, power, and routability. These are the ways that can develop the EDA symbolic relationship and quantum computing, where quantum volume is consist with all such of characteristics which are included in the qu- uh, quantum mech- uh, quantum computing. Thank you for having thank you for having this.